We've been talking about the different types of intermolecular forces, and now we're going to see the effects of the intermolecular forces. Of course, the very existence of solids and liquids at all is probably the strongest evidence that intermolecular forces actually do exist. But there are other properties that also arise from intermolecular forces, and we'll talk about each of these individually. These include surface tension, viscosity, and capillary action. We have two pictures here that demonstrate surface tension. This is a fishing fly, and it can sit on top of the water even though it is more dense than water. And here we have a paper clip sitting on the surface of the water, even though obviously it's made out of metal, and metal is more dense than water, and we would expect it to float. And so, how does it stay? We would expect it to sink. Why is it floating? It has to do with surface tension. Surface tension is the tendency of liquids to minimize their surface area. It's quantified as the amount of energy required to increase the surface area by a specific unit amount. So water has a surface tension of 72.8 millijoules per square meter. So that means that it takes 72.8 millijoules of energy to increase the surface area of a given amount of water by a square meter. We're not going to talk about surface area quantitatively, but it can be quantified. That's the word, quantified. It's bad when you start saying a word and you realize that you're not sure how it's supposed to end. So surface tension is what allows trout flies to float, as in this picture, what allows a paperclip to float on water. And you may not have seen that happen before. You can also do it with like a sewing needle. You have to have a very, very clean container, and you have to have clean water. If there's any soap or any contaminant in there, it will not work. So surface tension. When we look at this illustration here of liquid molecules, liquid particles, this is, of course, just a cross-section. But up here at the surface of the liquid, the particles at the surface interact with their neighbors to the side, and they interact with their neighbors below on the interior of the liquid. An interior molecule, though, can interact with molecules on all sides. So in this cross-section, we see the surface molecule interacting with 4 neighbors, the interior molecule interacting with 6 neighbors. So the interior molecule has a lower potential energy. It is more stable than the surface molecule. If we increase the surface area, if we were to put our hand into the water, that would increase the surface area. If something were to sink through the water, that would be increasing the surface area. Then we have to move more interior molecules to the surface. Because if the surface area is greater, then you must have more molecules here on the surface. Doing that requires energy. And nature tries to do things that minimize energy. So liquids tend to minimize their surface area because it's a lower energy, more stable state. Any questions? What we see is that surface tension decreases as the intermolecular force strength decreases. If the interaction between, let's go back to this picture, if these interactions are very strong, then going from 4 to 6 of them is a bigger energy difference than if these are weak. Does that make sense? Strong forces are going to resist a change in surface area more than weak forces are. The reason that water droplets are spherical is due to surface tension. A sphere is the geometric shape that has the smallest surface area per unit volume. Any other shape, so if you took, say 1 liter of water and you tried to minimize the surface area, the smallest surface area would be a perfect sphere. If you do any other thing, it's going to have larger surface area. So this is why water droplets make spheres. This is a fun picture from the space shuttle. This is a droplet of water in space where there's no gravity. When we see water dropping from a faucet, say, we see a teardrop shape, right? It's being distorted by gravity. But if you watch slow motion photography of that droplet as it falls, it'll vibrate a little, but it'll eventually settle into a sphere before it hits whatever it's going to hit. So any questions about surface tension? Another thing, property that depends highly on intermolecular forces is viscosity. Viscosity is the resistance of a liquid to flow. You can think of how thick a liquid is. Think of like maple syrup or molasses or honey. It pours very, very slowly, and water pours more quickly, right? Viscosity can also be measured quantitatively. The unit that it's measured in is called the poise. It's abbreviated capital P. It's 1 gram per centimeter second. We're not going to do anything with the quantification of viscosity, but it's good to just know what that is. Here in the table, they're measuring the viscosity in centipoise. So that's 1/100th of a poise. Viscosity is greater in compounds or substances that have stronger intermolecular forces. And if you think of, well, what's happening when a liquid flows, right? When you pour water, what's happening? Well, the molecules are having to move past each other and to flow out of the container. If the stickiness between them, the strength of the intermolecular forces is greater, they're going to be more resistant to flowing than if the forces are very weak. So high viscosity indicates that you have stronger intermolecular forces. Viscosity also, though, depends on molecular shape. When we have longer molecules, not only do we have an increase in the dispersion forces due to greater surface area contact, but we can also have the possibility of those molecules becoming entangled with each other. In this table, we're comparing several hydrocarbons, pentane, hexane, heptane, octane, and nonane. And these are all just straight chains of carbon with hydrogens on them. Each of these carbons is connected by a single bond, and there is rotation around a single bond. So these molecules are flexible, much like a piece of cooked spaghetti, right? They're flexible and they can twist around and get tangled. And so you can imagine that the nonane could get tangled with other nonane molecules quite easily. Whereas the pentane, being shorter, is not going to tangle up as much. It's like short hair versus long hair. Long hair gets very tangled and requires a lot of combing and brushing. Short hair just doesn't, right? We see a viscosity increase here from 0.24 up to 0.77. So the viscosity increases. We have two things going on here. We have the increase in molar mass, so increase in surface area, and we also have these long tangly molecules. Any questions? The viscosity also depends on the temperature. What happens to the motion of molecules as they're heated up? They speed up. They have more kinetic energy. They move more. They have more this thermal energy. And that allows them to overcome the intermolecular forces more easily. So a liquid at a higher temperature will flow more easily. And you could see this at home if you've ever had some, kind of old honey and it's like super, super thick, right? And it's like you're going to wait an hour to get any honey out on your biscuit, right? What if you warm up the honey? If you heat the honey up, it becomes very runny, and it's runny honey, and it comes out quite easily. Because at the higher temperature, there's more thermal energy, and the particles can overcome those intermolecular forces more easily. This has direct applications to your car's engine. Motor oil needs to have a particular viscosity. It needs to be, it needs to flow easily enough that it can go into the small spaces in your engine and lubricate things, but it needs to be viscous enough that when it goes up on the walls of the things that it needs to lubricate, it doesn't just immediately run down. We want it to coat and make a film there. You maybe have heard of viscosity breakdown, right? After a time, the viscosity of the oil can break down and it's not going to lubricate your engine very well. Also at high temperatures, it won't lubricate as well because the viscosity decreases. That's why they have all these different grades of motor oil. They are good for use at different temperatures. The modern motor oils, they've taken ideas of chemistry and done some really cool things. They use polymers in there that will coil up at low temperatures. So they'll make balls at low temperatures. And what did we learn earlier about the shape of molecules and those dispersion forces? If you have two spherical molecules, it's like two balls of Velcro, they can only touch at a little tiny point, right? And so they're not going to stick together very well. So at low temperatures, these polymers coil up, which lowers the attraction between them and lowers the viscosity. Motor oil tends to can get too thick at very cold temperatures, too viscous. And those polymers unwind at higher temperatures. At high temperatures, motor oil tends to become not viscous enough. Well, when they unwind and stretch out, then they become tanglier and help to increase the viscosity. And so you can moderate the viscosity change due to temperature in a motor oil by using these really cool polymers. Here's a table just showing the viscosity of liquid water at several different temperatures. At 20 degrees, the viscosity is 1. At the boiling point, 100 degrees, the viscosity is 0.28. Now, this is probably a change that you haven't really noticed. I think everybody's noticed the change in like maple syrup or corn syrup or molasses or honey or something like that at home, that when you heat it up, it pours much more easily. Water, the difference in viscosity between cold water and warm water, we probably haven't noticed, but it is a measurable difference. Any questions? Another property related to intermolecular forces is what's called capillary action. This is the ability of a liquid to flow against gravity up a narrow tube. So here we have an illustration of 3 different glass tubes. And these are just like straws. They're open on both ends, and the liquid travels up this tube. Nobody's sucking on the other end. You stick it in the water, and the water comes up it. This is a combination of 2 different forces. We have cohesive forces and adhesive forces. So cohesive forces are the attraction between the molecules in the liquid. This is the attraction of the water molecules for other water molecules. The adhesive forces are the attraction between the liquid and the surface area of the tube. There are also forces of attraction between the water and the glass. And depending on the type of glass or what kind of coating it has on it, you can alter the attraction that the water has for the tube. So the water, if we have significant adhesive forces, water molecule will be attracted to the glass, and the cohesive force basically drags other water molecules up with it. And so that causes the liquid to rise in the tube. How far it rises is going to depend on the size of the tube as well. In a very wide tube, the height will be very low. In a skinny tube, the height will be very high. And if you're interested in messing around with this, ask me during lab, and I can get some capillary tubes, and you can stick them in water and see it go. It'll come up. The idea of capillary action is also related to the meniscus. We've talked about the meniscus in lab and how when we measure things in a burette or a graduated cylinder, we need to measure to the bottom of the meniscus of the water because that's how the glassware was calibrated. If you look at liquid mercury, which would be really fun to actually play around with, but we can't because it's toxic. If you look at mercury, though, its meniscus bends or curves the other way. And this is because the relative strength of adhesive and cohesive forces is different. Water has a concave meniscus because the adhesive forces are stronger. The water is attracted more to the glass, and so it climbs up the edges. In mercury, the cohesive forces are greater. The attraction between the mercury atoms is greater. And so it looks like it's kind of trying to avoid the walls of the test tube that it's in. Any questions? The appearance of a meniscus is greater in a narrow tube. In a beaker, it's really hard to see. But if you look at different liquids like ethanol or acetone that have lower intermolecular forces, you'll see generally that their menisci are shallower, almost flat. Some things appear not to have a meniscus, they're just flat across. But water has a meniscus with glass. And then, if you use plastic or a different type of glass that's coated, you can also alter the shape of that meniscus.